This is part 2 of the walkthrough of the AQA GCSE Physics 2022 Higher Tier Paper 1. Question 7. Alpha particles, beta particles, and gamma rays are types of nuclear radiation. What does an alpha particle consist of? So, this is recallability now of our different types of radiation. So, our alpha particle is also known as a helium nucleus. So if we use our periodic table or our knowledge of helium, we was able to recall that helium has a mass number of 4 and atomic number of 2. So if it has an atomic number of 2, that tells us that it has 2 protons. But to find out how many neutrons it has, you would need to take that number 4 and subtract it from 2. So that tells us that it also has 2 neutrons. And that will be what our alpha particle is. It consists of 2 protons and 2 neutrons. Seven point 2. A krypton nucleus decays into a rubidium nucleus by emitting a beta particle. Complete the nuclear equation for this decay by writing the missing number in each box. So, we are given enough information to fill out these 2 boxes. What do we recall about beta decay? Well, what happens during beta decay is there's a release of a high-speed electron. But during that process, what actually happens is a neutron decays into a proton. So, if a neutron is decaying into a proton, that tells us that the atomic number is going to change, specifically increase by 1. So, if we've started out with krypton, which has an atomic number of 36, we are expecting our rubidium now to have a greater atomic number. So that means that our atomic number should be 37. But what happens to our mass number now? Well, a reminder of our atomic structure, inside of our nucleus, we should have neutrons and we should have protons. So, during this beta decay, as I said, a neutron is actually turning into another proton. Now, if you notice, there has been no change to the number of total protons and neutrons in our nucleus, because one is being replaced by another. So that means that our mass number should stay the same. So that means our mass number for krypton should also be 85. Seven point 3. Internal contamination of the human body means radioactive material is inside. Internal contamination of the human body means radioactive material is inside the human body. Explain how the risk from internal contamination is different to the risk from external radiation by a source of alpha radiation. 5 marks. So, if we do a quick sketch of the human body, what it's telling us now is internal contamination of a source of alpha. We want to compare that to the risk of external radiation from alpha radiation. So, our knowledge needs to be of what contamination and radiation is, which we've just kind of reminded ourselves now. Radiation is being exposed to some object which is emitting one of our 3 types of radiation. And then contamination is where an unwanted object is put in somewhere else. So we have reminded ourselves about these terms. We now need to think about alpha radiation itself. So what do we know about alpha radiation? Well, we reminded ourselves already that it's 2 protons and 2 neutrons, but it's really the properties of it. First property about alpha radiation is that it's the least penetrating. And what that means is that it can get stopped by paper or skin. Our other property of alpha radiation is that it's the most or strongly ionizing out of our 3 types. So that means that its ability to knock off electrons and cause something to be charged is very, very strong. So let's apply these 2 properties to our question now. Well, if we have alpha radiation which is outside of the body, so can be stopped by skin. So what does that then mean in terms of damage? Because we're thinking about risk, so it's got to be some sort of damage to the body. Well, because of that then, the damage to our body will just be really to the skin, which is not too bad. Let's compare that then to if we've got internal contamination. So for example, if we were to consume something that was emitting alpha radiation, well, we can't worry about skin anymore because it's past that. So we're then thinking about what's inside of us, our body, which is our organs, which is made from tissue. Well, the problem, as we said already, is the other property of alpha radiation is that it's most or strongly ionizing. So then what does that mean now? Well, if the alpha radiation is within our body, that means it can easily get absorbed by our tissue or organs. And then the problem with that then is it will have a greater chance of causing us some damage. Now, why does it have a greater chance of causing damage to organs? Well, because it can be ionizing, it could also lead to damage of the cells through mutation. But I think right now we have enough to get our 5 marks. We've mentioned the ability of alpha radiation to penetrate. We've said that because it's low, it can get stopped by our skin, so that's fine. We then talked about a second property, which has this ionizing power. We've said that then what that can mean is that the radiation can be absorbed. So then the actual risk is that it's going to be greater compared to the external radiation of damaging our organs. Question 8. A student determined the specific latent heat of vaporization of water. Figure 9 shows some of the equipment used. So we're given a power supply with a beaker containing water and a heater which is immersed in the water. This is the method used. Put 50 centimeter cubed of water in a beaker. Measure the mass of the beaker and water. Use a heater to boil the water and keep it boiling for 600 seconds. Measure the mass of the beaker and water after 600 seconds. 8.1. What measuring instrument should be used to measure the volume of water? 1 mark. Well, again, just like in our previous questions, we need something that has a scale that can allow us to measure volume of water. Easy option could be a measuring cylinder. 8.2. What is a hazard in the student's investigation? Tick 1 box. Well, safety goggles isn't a hazard. It's something that we would want to use to minimize the risks to us. Heat-proof gloves, the same. So we're just left with burns or boiling water. So let's go back to our method and see which one of these two is going to be. But we're taking some water, we're going to measure the mass of it. I'm going to use a heater to boil the water and keep it boiling for 600 seconds. So we are going to be boiling water. So the one that makes most sense for this practical would be boiling water. 8.3. The initial mass of the beaker and water was 0.080 kilograms. The final mass of the beaker and water was 0.071 kilograms. The energy transferred by the immersion heater as the water boiled was 25,200 joules. Calculate the specific latent heat of vaporization of water given by the student's data. Give the unit. Use the physics equation sheet. 5 marks. Another calculation. Looking at our equation sheet, one that is linking latent heat of vaporization, energy, mass. Can we find that? Yes, we can. Energy equals the latent heat of vaporization multiplied by the mass. So let's see what values we have. Plug them in. Energy transferred, yes, we've got that, 25,200. Our latent heat of vaporization, we need to find that. And our mass. Now, we're given an initial mass and a final mass. So what we want to find out is what is that mass that was used during this heating and boiling of the water. So our way to find that out is to find the difference between these two masses. So it would be 0.08, 0.071, and that should give us a value of 0.009. So rearranging again, we need to take that mass, move it to the other side. Opposite operation of multiplication will be division. So then that will mean that it will be 25,200 divided by 0.009 to give us our latent heat of vaporization. So that value is going to be 2800000. So we haven't gotten our 5 marks yet because we need to give the unit. So let's just add our units here for these values, and then it will help us to figure out our unit. So our energy here was in joules. The mass that we found the difference of was in kilograms. So all we need to do is use those and we'll get our unit. So it will be joules per kilogram. 8.4. Some thermal energy was transferred to the surroundings while the water was being heated. Explain how this affected the student's value for the specific latent heat of vaporization of water. 2 marks. So it's saying that energy was transferred to the surroundings. Let's go back to the setup and then let's see if that makes sense. So some energy during this heating process was transferred to the surroundings. So what is the problem then with that, and how is that going to affect the value for latent heat of vaporization now? Well, what do we want the energy to be transferred to? We want it to be transferred to the water. So that should be something we can definitely write there. So less energy is transferred to the water. Now, what does that mean for this value of latent heat of vaporization now? Well, if we look at our equation here, it's saying that less of this E is going to be transferred to water. So this value really is going down. So if this value of E is going down, then what will that mean for our value of latent heat of vaporization? Well, that value is going to go up because the mass will stay the same. So the value of latent heat of vaporization, the energy needed to change the state from liquid to gas, is going to be high now. And that's what we'll need to say for our second point. So we can just put LV for latent heat of vaporization. So the value of LV is going to be too high. 8.5. Some of the water evaporated before its temperature reached 100 degrees C. Explain how this affected the student's value for specific latent heat of vaporization of water. So our question is slightly similar to previous, but a different scenario now has taken place. So let us again go back to our figure. Some of the water has evaporated this time. So in this case, it's not energy this time. It's actually some of the water evaporating prior to it going to 100 degrees. So what that means this time now is that the mass is actually changing. Or really, the final mass is going to change. So that means our change in mass is going to be different. So what does that mean now for our value of latent heat of vaporization? Well, the change is going to be too different. So change is going to be too high. So now what does that mean in terms of LV? Well, LV is now going to be too low. So essentially the opposite a little bit. This value is going to go up, the change in mass. So then this will now be too low. So our first point that we can say now, the change in mass is too high. So the value of LV is too low. Question 9. Figure 10 shows a girl doing an experiment to determine her power output by running to the top of some stairs. 9.1. The mass of the girl was 60 kilograms. The height of the stairs was 175 centimeters. The girl ran to the top of the stairs in 1.40 seconds. Gravitational field strength is 9.8 newtons per kilogram. Calculate the power output of the girl. Use the physics equation sheet. 5 marks. Okay, so this is our first example of our compound questions, meaning that we have to use multiple equations here to generate our final answer. So, directing us to use the physics equation sheet. So let's just check and see what quantities we're given. We're given a mass, we're given a height, we're given a time, and we're given gravitational field strength. We need to find power. So, checking our physics equation sheet, do we have an equation that's linking mass and height somewhere? Yes, we do. And that equation is to calculate gravitational potential energy. So, gravitational potential energy is equal to mass times gravitational field strength multiplied by the height. So, we haven't yet taken into account our power and our time. So let's see if there's an equation in our equation sheet that has those two taken into account. And there is. And that equation is power is equal to energy divided by time. So, do we have enough now to figure out anything right now in this question? Well, we're not given gravitational potential energy, so not yet. We're given a mass, we're given gravitational field strength, and we're given a height. So we can work out this energy, actually. So we would need to find this first. But remember that energy is not created or destroyed. It's transferred only from one form to another. That's our conservation of energy. So that means that whatever value that we generate here, we can actually put that into this equation. So that's what we should do first. We should calculate gravitational potential energy and then use that to eventually find the power. So let's do that. So our mass is 60 kilograms. Happy with the unit. Our gravitational field strength is 9.8 newtons per kilogram. Happy with the unit. Looking at our height now, it says 175 centimeters. The only problem though is that we need to get that to our standard unit, which is in meters. So to convert centimeters to meters, we need to divide by 100. So 175 divided by 100 should be 1.75. So if we calculate that now, that will give us a value of 1029. So we've got 1029, and that will be in joules, of course. As we can do now, we can now plug that into our equation to calculate the power because we've got the time already. So power is equal to energy, which in this case is 1029, divided by the time, which is 1.40. And then that will give us a value of 735 watts. So that's the way for doing these type of compound equation questions. Try and figure out what equation you can start with, what information have you got enough of, and then see if there's an equation that links it, and then continue on. 9.2. The total power output of the girl was greater than the answer to question 9.1. Suggest 2 reasons why. So they are saying that this value that we've calculated here of 735 watts, the output was actually greater. And why might that be the case? Well, if we think about what's happening, the person is running up the stairs. So for the person to run up the stairs, there needs to be kinetic energy. But then that kinetic energy is actually going to then be transferred to gravitational potential energy. But if you notice, at the beginning of the experiment, the girl is standing still. And then she moves. So realistically, what is actually happening is there's going to be an increase in the kinetic energy, and then that will lead to an increase in the gravitational potential energy. So if there's an increase in the kinetic energy, that should mean then that there'll be an increase in the power. So that could be a reason why the power was higher. So you could say for the first point that girl increases her kinetic energy. Okay. What else could be different now? Again, we've got to think about energy. So when the girl is running, what else could be taken into account? Well, again, for there to be a transfer of energy, there is probably going to be something wasted. And that, again, most of the time for any sort of transfer, it will be thermal energy. So as this girl runs, there will be some thermal energy which is wasted, meaning giving it to the surroundings. And again, that can contribute to the total power output. So some energy is transferred to surroundings. 9.3. A boy took more than 1.40 seconds to run up the same stairs. The power output of the boy was the same as the power output of the girl. What conclusion can be made about the boy's mass? Mass greater, mass lower, mass the same. Well, we know definitely it cannot be the same. Why? Because if it was the same and the power output was the same, then it would be the same time. So it cannot be that. So why would it take the boy to run more than 1.4 seconds even if the power is the same? Well, if the mass was lower, technically the boy should run faster, so it should take less than 1.4 seconds. So if it was greater, that should make the most sense. Question 10. Figure 11 shows a student launching a toy aeroplane. To launch the aeroplane, the student pulls on it to stretch the spring and then releases it. 10.1. Just before the toy aeroplane is released, the spring has an extension of 0.12 meters. The mass of the aeroplane is 0.02 kilograms. The spring constant of the spring is 50 newtons per meter. Calculate the maximum speed of the toy aeroplane just after it is launched. Use the physics equation sheet. Give the unit. 6 marks. So, I think we've got another compound question again. So again, let's do the same method. Let's use our physics equation sheet, and then let's see what equation we can use. So is there an equation that is linking extension, mass, and spring constant? Yes, there is. Let's recall it. Elastic potential energy is equal to 0.5 multiplied by the spring constant multiplied by the extension squared. So, what haven't we used now? Speed. So, what equations do we have that's linking our speed? Well, the problem is that we'd have to think about what else in our question we might be able to link it to, because this is the only other value or quantity that we don't have or have not used yet. So looking at our speed, it's going to be difficult for us to link that to spring constant, but we can link that to the mass using our equation for kinetic energy. So kinetic energy is equal to 0.5 multiplied by mass multiplied by speed squared. And I think that would make sense because we're looking at a toy aeroplane. The spring is going to contain some elastic potential energy store. And then as that released, we can then think that the toy airplane is going to move. So that would be where the kinetic energy comes into play. Again, thinking about our law of conservation of energy, the elastic potential energy will then be converted to the kinetic energy store. So that would make most sense here. So first thing that we can do then is we can calculate the elastic potential energy. So getting our marks, we can multiply 0.5 by our spring constant 50, multiply by 0.12 squared. If we plug that into our calculator now, to simplify, we should come out with a value of 0.36. So, one more time, our elastic potential energy will be converted to kinetic energy. So we can say that the elastic potential energy is equal to our kinetic energy. So that means now that this 0.36 joules that we just calculated will actually be equal to 0.5 multiplied by the mass multiplied by the speed squared. But looking back at our question, we are already given a mass. So we can add some more. 0.5 multiplied by 0.020 multiplied by speed squared is equal to 0.36. So what we can do then is we can just simplify further so we can get a clearer picture of what our final answer is. So simplifying this further now, we will have here 0.36 is equal to 0.01 multiplied by v squared. So that means that 0.36 divided by 0.01 will be equal to our speed squared. So that means our 36 is our speed squared. However, we are just focused on the speed, not speed squared. So that would mean we'd need to take this 36 and square root it to find our value of speed. And the square root of 36 will be 6. Our unit of speed typically is meters per second. And there will be our points for 6 marks. (10.2) As the aeroplane moves upwards through the air, there is a decrease in the something energy of the aeroplane. 1 mark. So, we saw that our aeroplane is going to get released and then it will move upwards through the air. Well, as our aeroplane moves, what will be happening? Really, as it goes through the air, there will be a force that will be applied to the aeroplane. And that force will be air resistance. Now that air resistance will be acting in the opposite direction to the plane moving. And what it really will be doing is it will be slowing the plane down. So if the plane is moving this direction, our force of air resistance will be in the opposite direction, trying to slow it down. So what does that actually mean then for our kinetic energy? That would actually be decreasing. Remember, it cannot be elastic potential energy, because that would have been converted to our kinetic energy stored by that point. So our most logical answer here now is going to be kinetic energy. 10.3. Give one factor which would increase the distance the toy aeroplane travels horizontally before hitting the ground. 1 mark. Well, how could we really keep this plane in the air for longer is what the question is asking. Well, it's the toy aeroplane that we're thinking about. I think we need to think in terms of not changing this aeroplane. It's wherever the toy is, we need to keep that the same. So what other things could we really change? Well, commonly if you want to throw something in the air and you want that to actually be in the air for longer, you really want to change the angle at which you release it. So by aiming the angle a little bit higher perhaps, it might mean that the aeroplane will be in the air for longer. But remember, you can't change the angle too much, because if the aeroplane was now in this direction, then it would not be staying in the air for much longer. So you want to change the angle just a small bit, so then it can remain in the air for longer. So change the angle that the plane is released from. And if you look carefully at our question, it says increase the distance. So we don't really want to decrease the angle that it's released from. We want to increase the angle that it's released from. So I think our best way we can say change the angle is by increasing the angle. Question 11. Figure 12 shows some hair straighteners. Hair straighteners contain heating elements. So figure 12 is showing us a picture of a hair straightener. 11.1. When the hair straighteners reach normal operating temperature, an LED turns on. Draw the circuit symbol for an LED in the box, 1 mark. Well, remind ourselves what is an LED standing for. It's a light emitting diode. So we want this light to be given out when the hair straightener reaches its normal temperature. So our circuit symbol for an LED, to do simple recall, should be 2 lines with a circle separating them. And then we want to draw a triangle in our circle with that line. And this represents our diode right now. A reminder just to recall with your circuit knowledge, our diode is to force or prevent the current from going in 2 directions, so forcing the current to go in 1 direction only. So what is going to make this now become a light emitting diode or LED? We need to show 2 arrows going away from it to show that light is given off, and that's our symbol for our LED. Figure 13 shows the circuit diagram for the hair straighteners. Each resistor represents a heating element. The power output of the hair straighteners can be changed by closing different switches. Figure 13 showing us our parallel circuit now. And here are 6 resistors with 2 in series with 3 pairs in parallel. 11.2. Why do the hair straighteners not turn on when only switch S2 is closed? So if this was actually closed now, why do we not get the hair straighteners turning on? Well, let's think about what's happening during the power supply then. We should get our electrons being transferred, moving around our circuit. However, it can't move through S1 because there is a gap in the circuit. So that means that it will be not able to get to S2, and then from there it will not then be able to get to S3. So the problem is that the circuit is not complete. There is a gap in the circuit which is preventing electrons from moving. So we need to just formulate our answer to say that there is a gap in the circuit. .3. The hair straighteners have a maximum power output of 120 watts. The energy transferred to the hair straighteners to reach normal operating temperature is 3.6 kilojoules. Calculate the time taken for the hair straighteners to reach normal operating temperature when operating at maximum power. Use the physics equation sheet. 4 marks. So, looking at our equation sheet, what equation is linking energy, power, and time? We've used it already in this paper. So, energy equals power multiplied by time. What information is given to us? Well, we're giving us a power output of 120 watts. So you can plug that in straight away. We need to calculate the time, but energy is given, which is 3.6 kilojoules. We need to again convert that to our standard unit of joules, multiplying that by 1,000, so that will be 3,600. So to leave t time on its own, we need to move our 120 to our other side. Opposite operation to multiplication is division. So 3,600 divided by 120 will equal our time. So that means our time should be 30 seconds. (11.4) Figure 14 shows the hair straighteners circuit with switch S1 closed. Switch S2 and S3 are then closed at the same time. Explain what happens to the power output of the supply. So we've got S1 closed. So let's just box our S1 and see what is going on there. Well, when the switch is closed for S1, we have our circuit which is working, part of the circuit which is working. But remember that these are resistors, and these resistors are in series. So what we would need to think about is, how are these resistors going to affect the circuit? Well, the resistors are in series, so the total resistance of resistors in series is adding them up. So R1 plus R2 is equal to the resistance total. So if the resistance is going to be increased now, what does that do to the current? So an increase in resistance causes a decrease in the current. So the problem that we have to think about now is that's not the full question. S2 and S3 are also closed. So that obviously means now that these resistors are also taken into account now. But these resistors are in parallel compared to each other in S1. So what we've got to think about then is, how is the total resistance in parallel going to work? Well, what we must know is total resistance in parallel. The total resistance in parallel is smaller than the smallest individual resistor. That is a rule. The total resistance in parallel is smaller than the smallest individual resistor. So that means then that if we had a resistor, let's take this one here, which was 2 ohms, that would mean then that the total resistance would be smaller than 2 ohms. So that means then, if the resistance was smaller, that would mean the current would be higher. So what does that do to the power output of the supply? So then we got to think about our equation that links power, current together. Again, we've mentioned that equation. Power is equal to potential difference times by current. So if our resistance is lower, our current is higher, what does that do to our power output? That will increase it. So we just need to say all of that in words to gain our marks. So first thing that we need to say then is, what does that do when the switch S2 and S3 are closed? The total resistance decreases. What does that total resistance do? If it's lower, it causes the current to increase. And then if the current is increased in the circuit, that will then cause the power output to increase.